do it. Good afternoon. Last time we spoke about hybridization of atomic orbitals. And we did this because the valence bond theory allows us to do this. We can hybridize these orbitals, these atomic orbitals, into hybrid orbitals that can accommodate different geometries. And you know, so far we only were able to do P and S combinations, and there was only the possibility of 90 degrees essentially angles between the atoms in a molecule. By doing the hybridization, for example, we have a steric number 2, we combine one s and one p orbital to an sp orbital, actually to two sp orbitals. If we have one s and one p, so that's two orbitals, we have to end up with two orbitals, to two sp orbitals, and with this we have a bond angle of 180 degrees, and we can accommodate here, binding to here, that's the central atom, it can bind here and can bind here. So one thing you have to remember is that you have two p orbitals that are not hybridized. You have them left, okay? They might not be used, but they are there, all right? If you have one s and one p hybridized to sp hybrid orbitals, then you have two p orbitals on each of the atoms, which is not hybridized, okay? So that is very, very important. And if we want to accommodate steric number 3, can you hear me in the back? Yeah, good. Steric number 3, we need one s and two p orbitals to get a trigonal shape here, and this would be then sp2 hybridization. How many p orbitals do we have left? One, okay? Don't forget that, all right? It just doesn't fall under the table, that p orbital, okay? It is still there, all right? So you can, with this, then accommodate 120 degrees. Now, if you have steric number 4, you have 4 neighbors, so you have to go into 4 directions with your orbital shape. I'm talking about atomic orbitals. We haven't done any binding at this point. The atomic hybrid orbital would be 1s and 3 p's, so you make 4 sp3 orbitals, and they point in 4 different directions in space, and this gives you then the tetrahedral configuration. This is how you can bind tetrahedral. So how many p orbitals do you have left? None. None, okay? All right, so we have talked about this, and now we want to talk about steric number 5 and steric number 6. We are out of s and p orbitals, and we still need to accommodate steric number 5 and steric number 6. So we need to go to the d orbitals. Of course, you only can do this with starting in the third period, with atoms in the third period, where you have possibly d orbitals, okay? So in this case, for example, iodine trifluoride has 1, 2, 3, 4, 5, steric number 5, and this would be a trigonal bipyramid. And so we would use sp3, but we need one more. So we would use dsp3, or sp3d, however you like it, okay? dsp3. How many d orbitals do we have left over? 4 d orbitals you have left over. That's very important. So with dsp3 is your hybrid orbital. You can accommodate this trigonal bipyramid, and with this case here you put the fluorine in here, for example, here, here, and here, and the free electrons are here. Okay, the fluorine would bind here. You're not going to put it in, but here are the free electrons. So now we want to accommodate steric number 6. I'm a little too fast. Phosphor pentachloride would be also a dsp3 hybridization on the phosphor. What do you think you have on the chlorine? What do you have on the chlorine? 1, 2, 3, 4. What hybridization would that be? sp3, exactly. That would be sp3, for example. So steric number 6 is octahedral. So you use 2 Ds, 1 S and 3 Ps. How many Ds do you have left? 3, that's important. With this you can accommodate this geometry, and you would, for example, a sulfur hexafluoride. They would bind here to the sulfur would be here, and these are the lobes of the sulfur, and they bind then to the lobes of the fluorine. Or xenon tetrafluoride, you would have 2 free electrons in here. Here, this is how this looks like. This is phosphorus, and this is 1, 2, 3, 4, 5. So this is steric number 5, dsp3, hybridization on the phosphorus. The yellow is the phosphorus. Now, what's the chlorine dehybridization? sp3 again, okay? So you have and what kind of bond would you make here? This is an dsp3 and this is an sp3. What is this, a sigma or a pi bond? Sigma, excellent, all right. And this would be the atomic orbital d2sp3, and this would bind to the fluorine here, 2, 4, 6 coordinated fluorines, or 4 coordinated fluorines and 2 free electrons here. So with this, we're going to quit with this. Not forever, but just for now. This will be, of course, in the midterm. This will be in the final. But we're going to walk away now from binding theories and binding as such. And binding was sort of on an electronic level, on a very small level. Now we go to macroscopic observations. And we're not going to try to understand it on a microscopic level. Yes, we will eventually understand it on a microscopic level. But today, we're just going to look at parameters that are very large parameters in terms of molecules. So we look at the large number of molecules, and gases have a large number of molecules. And we treat these gases as if they would be perfect. What's a perfect gas? We all are perfect, but a perfect gas, we don't know what that is, okay? So a perfect gas we define as an ideal gas, and we can treat many real gases as so-called perfect or ideal gases. Because we say the molecules or the gas atoms or the gas particles are so far away from each other because they're in a certain volume that they don't interfere with each other, okay? And so there is no interaction between them. And each molecule behaves like it would be by itself in that space. So this is the condition for an ideal gas. Doesn't exist, but helps very well to explain many behaviors of gases, especially at moderate and high temperatures. At low temperatures, it's a little bit more difficult, and we talk about this at another time. So there were, in the 17th century, there was Battista Torricelli from 1608 to 1647, and he was a student of Galileo. And they didn't know, many of the scientists didn't know what we know now, especially 400 years ago, about 400 years ago. And so we are standing tall on their shoulders, but we have to really admire them, how they came to this. One of the things they were considering at the time is, you know, you have this, must be a gas or something, what we're breathing, and the question was, does this exert any pressure? How would I be able to measure that, and how would I be able to show this? And Torricelli, he used a glass tube of which he pumped out the air. Okay, he had a little pump. They knew how to make a pump. He pumped out the air. And then he put his thumb on the bottom of the glass tube, pumped it out quite well, and turned it around and put it in a pool of mercury. Okay? Put it in a pool of mercury, and what he's seeing that's the pool of mercury. You see that the mercury goes up here, inside that empty glass tube. There's no air in there. So what he concluded is that the air must be pushing on here, and the pressure that it exerts on this can be measured here, how high that mercury goes up in the tube. And this is what we know now is a barometer. And he invented the barometer. And so this is, of course, dependent on the density of your material. If he would do the same thing with water, he would need a column of 10.3 meters or 33, 34 feet nearly long, because one atmosphere, that's the pressure we are at here, one atmosphere will push a column of water 10.3 meters high up. Would be a very inconvenient barometer, okay? You have to run around with a column of 10.3 meters to measure the pressure. So you have a little thing like this here, and if you shape it right, then you can measure the pressure with a mercury barometer, and nowadays it's even done very differently, piezoelectric, for example. So with this, we have the standard atmosphere, that's what we are here, one atmosphere, one ATM. This equals 760 millimeters of mercury, or 76 centimeters of mercury. And this is also 760 torr for Torricelli, so 760 millimeter of mercury or 760 torr. Or in the Pascal system, which is much smaller units, in the SI system, is 100,325 Pascal, okay? So, if you, for example, some of you come from homes where they have a well. Now, if you dig a well in your yard and you don't go deeper than 10 meters, maximum is 10 meters, you don't need a pump, because the air pressure will put this water right up there to the surface if that's what the air pressure one atmosphere can do. And if you are deeper than 10 meters, you have to evacuate, essentially, your tube to allow the water to come in. That means you have a little pump which pumps the water up. That's what we're doing, pumping the water up. And so if you're deeper than 10.3 meters, then the water can't come up by itself anymore. All right? So the other thing was that Torricelli noticed is that depending on the weather, he found small changes in that pressure. And there were low pressure days, and there were high pressure days. And we know now what those is, a high pressure system and low pressure system. And pressure always goes from high to low. It never goes from low to high. That's the important part. The same is for temperature. Okay? Temperature goes never from low to high. We talk about this in thermodynamics. Okay? So we know that pressure is the force on a certain area, on a unit area. Now let's go to Ireland and let's visit Mr. Boyle. He was an Irish physicist. He lived from 1627 to 1691, about the same time than Torricelli. He got a little bit older, and they didn't communicate with email. They didn't communicate, period, end. And Boyle found out if you have a gas and you exert pressure on this, there's a relationship between the volume and the pressure of a gas. And what he found out is, and many of you have done it. You had a syringe, for example, a little syringe, and you tried to hold it shut in the front, okay? And though at the beginning you can easily push it in, but then you have to push harder and harder and harder. At the end, it's so much pressure that your finger doesn't hold, it comes out, okay? So I'm going to explain to you this in a second, this phenomenon. If you have, for example, this is your syringe. We will have this picture of this cylinder, a closed cylinder with a plunger here, or a piston, where you can compress a gas, or it can go decompress a gas in the opposite direction. We will have this quite a bit. So here, yellow is our gas, and so we have just pushed this down, and we used a certain amount of pressure to push it down, and to come to here, if I plot the pressure here and the volume here, I needed more pressure to decrease the volume further. And I need even more pressure to get it smaller. And this you have at a fixed temperature. It's called a pressure-volume relationship. That's an isotherm because it's a fixed temperature. And what you know is the pressure times the volume is a constant. If the pressure increases, the volume decreases, and vice versa, okay? And this is a constant, but only a constant at a fixed given temperature. The constant changes at different temperatures. Now, let's see what that constant is. So what we can do, we bring this V over here. then we have P equals a constant divided by V. So we plot 1 over V here and P here, and then we should have a straight line, and we know what the slope of the straight line is. That's the constant. And this would be for temperature 1, and you have now a linear relationship, and you have a different constant for another temperature. It will go P and 1 over V 0, it will go through 0 here, but it's a different slope here because the constant difference, and this is expressed the same way here, that the constant is different. That's why the isotherm, the line by constant temperature, is different than at this temperature. Okay? So this was Boyle. Actually, Boyle, if I could have the picture on me, please. Boyle wasn't really necessarily interested in pressure-volume relationship. As it's so often, the scientists, they want to have a much bigger picture. And he wanted to find out if living creatures need this air to live. They didn't know anything about it at the time. And now it sounds cruel to us because there were no animal rights. There were barely human rights, okay? And so that's very different at the time. So he said, okay, he had already a pump that he can suck out of the air out of a container. So he made a container, a round container, put his pump, sucked the air out, and then immediately put in the little mouse, okay? And then he looked at it and pulled it out. Okay, mouse dead. Mouse dead, all right? So now, to be a good scientist, you can't say that the rat will die or the dog will die if you do the same. You have to do it, okay? It sounds cruel, but it's the truth. We're standing on the shoulders of giants. We wouldn't know all this stuff if they wouldn't have done that. So he put the rat in there, pumped it out, opened it up, dead, okay? Then the snake and the turtle and so on, dead, dead, dead. And so don't laugh at them, okay? And they were not cruel at the time. Maybe they were, but without their knowledge, we wouldn't know what we know now without their experiments. So when he did take a short break from his suffocation experiments, then he decided that P times V equals a constant, okay? P times V is a constant, and this is Boyle's law. Now let's do a little demonstration about Boyle's law. The first one, I need Karen for that. I hope she hears me. I have some marshmallows, some very nice little morsels here. Tasty, aren't they? You like them? Please have a marshmallow. Okay. I hope Karen comes. Can you get her? You can go there. Go there. Okay, anybody wants any marshmallows? Good catchers? One more. Lighter, okay? Lighter. Anybody else? Good. Wow. Now, since Karen is I don't know. All righty. Not so bad for an old man. Oh, yeah, there it is. One more. One more. Good. So, what we have a vacuum pump here, and we have these marshmallows. They taste so good because they have sugar and fat. And the other thing is, anything sugar, fat, and salt tastes good, okay? That's how it is, unfortunately. And there's air pockets in there, which makes it so compressible and so nice and fluffy. So what we're going to do, we're going to put them in here. And now we're going to do P times V is a constant. We're going to decrease the pressure now. And watch them closely. Karen will pump first. She switches on her vacuum pump. She pumps the air out. Woo! These babies rise. You see that? Okay. So now, see, they're slowly destroying themselves. That's the problem. Okay? And now she lets it go back. See, they came up, and then she lets the pressure in again. They deflate. And they didn't deflate again to the original shape because they have these little membranes in there. And when they were expanding, they were breaking these membranes. Let's see if they still have the same taste. Anybody? We cleaned this here. Once every 10 years we clean it. Okay, good. This was Boyle's law. in action, but actually we're using it every second, Boyle's law. If I breathe in, I have these flappy things, they're called lungs. They're nothing but pieces of flesh that have a high surface area in order to absorb as much as possible air. But they are passive organs, they're not active organs. So in order to get air into my lungs, I use my diaphragm. The diaphragm is a muscle, and I'm expanding my chest cavity. Okay, and now I have a much bigger chest, so the volume is bigger, the pressure lowered. Now the air from the outside can rush into my lungs. Okay, and when I breathe out, I decrease that cavity, and the pressure goes now from the lower to the higher gradient. Okay, this is how breathing goes. Let me show you a little experiment. I have a smoker here, no, a lung here. If I could have the light, and very nice picture up there. Larger, please, a little bit. From the front, take the front camera, please. Yeah, and now go closer. So that you see my head maybe still. Yeah, a little bit more maybe. Okay. So you see these lungs, this is the diaphragm. Okay? Now I'm breathing in now. You see that? Okay. So I have to increase the volume in here, or decrease the pressure, so the air rushes in from here. So now I do the opposite. The air comes out. The air comes in. The air comes out. Now you can hear the baby breathe. Luke, I'm your father. Okay. So the diaphragm in action. All right. So let me get rid of that microphone here. And let's continue. Who else did we have? So we talked about Boyle. So we can talk quickly about the compressibility. Did I eat my clicker? No, huh? Okay, let's talk about the compressibility. What this is here is if you have this curve P over V, the change is the differential of the curve essentially, okay? You have the change in V over the change in P. So that means that here, in order to change the volume change, you need a very small increase in pressure to change the volume from here to here. So you have a relatively large volume change because you had a large volume to begin with, but a very small pressure change. Now here, this would be this case here. This was the first case. This case here, this would be the volume change. This requires a larger pressure change already. And the curve gets steeper here, as you see that. So if we go to here, then we would have a very large pressure change for a relatively small volume change. See that? How large that pressure change is? And the resulting volume change? Very small. And this is expressed in the so-called compressibility. And this is, of course, different for certain gases at times. So, now I have to talk to you about diving, all right? Who is a diver here? Anybody? Any divers? Very good. So what I tell you, you are not going to do, but you know that if you have 1 atmosphere at the surface and you go 10 meters, every 10 meters you get 1 atmosphere. Remember that water column we had? Every 10 meters, the pressure increases by 1 atmosphere. So at 10 meters, you have 2 atmospheres. At 20 meters, you have 3, at 34, at 45, at 56, and so on. So you have very strong pressure increases. Of course, you can't go down there without equipment because you have this tremendous pressure on your body. So what you would have to do, you have to breathe in compressed air, which neutralizes this pressure. So if you are at 2 atmospheres, 10 meters down, you have to breathe in the equivalent, I think you have to breathe in 2 atmospheres, okay? And this is called scuba diving, self-contained breathing apparatus, and it was invented by Jacques Cousteau. And he was tired of not going down to the depth, so I have to have these huge helmets on there to get down there and pump it in. So he invented that, and with this, people can go deep down. Now, let's assume you do something which no diver does. You don't breathe out while you come up. So you're down there at 60 meters, and you want to go or at 50 meters, and you want to go to 30 meters. So you have a certain volume, and you don't breathe out. So how much would the volume in your lungs increase, or the pressure increase in your lungs? Let's go with volume or pressure. It's the same, essentially. So the question I'm asking you now, if you go from 10 meters to the surface, so you do an ascent from 10 meters to the surface, or from 20 meters to 10 meters, or from 50 to 30 meters, what do you think about that? Well, give me the answer, and the answer is not the obvious. I can tell you right now. You need to use physics. P times V is a constant. If you have one pressure and one volume, that equals a second pressure and a second volume. Obviously, you need the ratio of the two pressures. You go from volume 1 to volume 2, or from volume 2 to volume 1, depends on how you want to define it. You go higher, so your volume changes, okay? How much does it change as a function of pressure? Can you turn me on a little bit louder, please? Just a little bit. Not so high that they fall off the chairs in the back here, but a little bit more. Is that better? Seem to speak very quietly today, not my style usually. Okay, there is a majority because I said it's not the obvious. But some of you may know the answer correctly and have clicked also correctly. So I think you should discuss this with each other and then give me a corrected answer for some of you, please. Please have a discussion. No guessing. Write down. Write it down. No guessing. Yeah, that's correct. I hope that you did the calculation. And because in the exam, there's nobody said, don't take the obvious, okay? So you have correctly, I mean, most of you have correctly found out that if you had 50 meters, you had 6 atmospheres. You go to 30 meters, that's 4 atmospheres, okay? So what you have, P2 times V2 is P1 times V1. That means V2, that's the volume. V1 is the one where you start out. V2 is the volume when you go up. V2 is P1, that's 6 atmospheres. Let's go with this case, 50 to 30. 6 divided by 4, so this is, what is it? 1.5 times the initial volume, okay? So the volume at 30 meters is 1.5 times the initial volume at 50 meters. Now let's do the next one, 20 to 10. So you have P1 is, let's see, this is probably written here, okay? So this we established. This one, 20 to 10, is 3 divided by 2 times V1. What is that? 3 divided by 2, 1.5. It's the same, okay? But if you go from 0 to, from 10 meters to 0 meters to the surface, what would that be? That would be 2 divided by 1, and you have now twice the initial volume. And with this, of course, you don't hope that you hold your breath when you come up to the surface, that it can equilibrate. Because for some people, they dive down to 10 meters, actually. And it hurts a little bit sometimes without breathing gear. So with this, A was the answer. So let's come to Mr. Charles and Gay-Lussac. They lived 100 years later than these other two guys, Boyle and who was the other guy? Torricelli, Boyle and Torricelli. Thank you. And so the guy Charles was a Frenchman. He lived from 1746 to 1823. And he was the first person to make a solar balloon flight by filling a balloon with hydrogen. He obviously was a non-smoker. All right? Never mind. So what this guy, Charles, or Sir Charles found out is there's a relationship between the volume and the temperature. If you increase the temperature, the volume will increase. If you decrease the temperature, the volume will decrease. And there's a linear relationship between the volume and the temperature. Depends on the gas. The gas will give you a different slope, for example. Let's see, that's a different slope. But now think about it. If there's a relationship between the temperature and the volume, we can measure the volume and get a temperature. So the temperature 0 would be at 0 volume if I have no more volume. And as I increase the temperature, the volume increases. So this would give us a new scale. And Mr. Kelvin came along and said, I'm going to use this as a temperature scale. And I say, there's no way that we can reach a volume of 0. That's the first thing. The next thing he said, or this was Charles maybe, he said, there are no negative volumes. Okay? So that means there is a lowest temperature because there are no negative volume. We don't have negative volume. The volume can only be 0 or positive. No negative volume, so there is a limit in temperature. That was a very, very important step. And with this, he said, okay, we have this absolute temperature, which is minus 273.15 Celsius. Okay, and with this we get a new temperature scale. It's the Kelvin temperature scale, and it's just Kelvin, large K. No degree sign or degree Kelvin, just Kelvin. In degrees Celsius, you may usually make degrees Celsius. So degree Kelvin temperature is the temperature in Celsius plus 273.15. Okay? From now on, listen very carefully. From now on, every calculation that you will do with Kelvin temperatures. Think about this, even today, all right? So now what we can do, we've seen that Avogadro's law, the volume was proportional to the number of atoms we have, okay? Remember at the very beginning when we said 1 mole of an ideal gas at standard temperature and pressure has always 22.4 liters. It doesn't matter what that gas is. It's an ideal gas. It has a mole of helium, a mole of hydrogen, a mole of nitrogen, a mole of oxygen, has always 22.4 liters. So it's just proportional, the volume is proportional to the number of particles, the number of gas particles. That's the first one. That was Avogadro's law. The second law we heard about was Boyle's law, that the pressure times the volume is a constant, or the pressure is a constant divided by the volume. Proportionally, pressure proportional 1 over the volume. And the third law is Charles' law, where we said the volume is proportional to the temperature. We have just demonstrated this. And with this, we could, maybe I show you, before we do something else, I show you another experiment to show you that the volume is proportional to the temperature. I have here, if I could have the front camera, please. I have here liquid nitrogen in this container. I'm going to pour that in. Liquid nitrogen is about minus 197 degrees Celsius or minus 77 Kelvin, something like this. No, 77 Kelvin, not minus. 77 Kelvin. And so it condenses here. So I have this balloon. It's not going to burst or anything. I have this balloon. So that this balloon has this shape is because it has a certain pressure. The gas atoms or molecules or particles, they hammer against the wall. And so they have a certain velocity, obviously, a certain momentum, which is a function of the temperature, but we will learn this later. And so that's why it has this shape. There seems to be some kind of an equilibrium between the outside and the inside. And so now I can decrease the temperature on this by putting in this in liquid nitrogen. What should happen to the volume? Should get smaller. Okay, let's do that. Takes a little while because I can touch it, the surface. There we go. See it getting smaller? So the temperature decreases, the volume decreases, directly proportional. Let's get a little smaller. See it? Now I let the temperature come up again. Very nice shot. Good shot. There it is. It shouldn't burst. That's why I handled it so carefully. Of course, you smash it in 1,000 pieces if you do that. You can do this with a banana. Put it in liquid nitrogen and then smash it in 1,000 pieces. You never heard that here, okay? And then walk away. Okay, so let me put a little more heat in there. Ooh, it's cold. What's going on? I must have a leak. Yeah, it has a leak. See, there's the leak. So let's do this with Fido then. Let's shrink Fido. Let's shrink Fido. There, Fido is shrunk. Now let's come back, Fido. Fido comes back to life. Okay, there's Fido. And Fido didn't leak. Very fortunate for us, okay? All right, good. So now we combine Avogadro's laws, Charles' laws, and Boyle's law to the ideal gas law. And the ideal gas law is, you have heard many times. First, I now want to talk at the standard temperature and pressure. So this is at 1 atmosphere, and how many degrees Celsius? How many degrees Celsius is this? 0 degrees Celsius, not 25, the standard temperature and pressure. So P times V equals N times R times T. That's the 3 laws we have combined here, all 3 laws. And of course, there are partial pressures. If you have 50% of helium and 50% of hydrogen, a mixture, and the helium is at 0.5 atmosphere, and the hydrogen is at 0.5 atmosphere, together, they are at 1 atmosphere. Okay? So that's why you have partial pressures. That's the partial pressure, and this is the partial pressure of that species here. That would be the pressure of the helium, and that would be the number of the helium atoms, or the pressure of the hydrogen and the number of the hydrogen molecules or moles, for example. So this is partial pressure. Now, P times V is N times R times T. We have the pressure in atmospheres. Now, be very careful that you use the right units. You always have to do an analysis of your units, okay, when you do a calculation. The volume you have in liters. N you have in what? Number of moles in moles. R is a constant. That's the ideal gas constant, or the Renault constant. That's why Renault with R. And this is 0.08206 atmospheres times liters divided by Kelvin divided by mole. You will be given that, but you need to be able to juggle this and use the right one. Or 8.314 joules per kilo per mole. That's also you can use. You need to use the correct one. And then T is the temperature, and it's the absolute temperature in kelvins. If I give you Celsius, you have to calculate it, recalculate it into Kelvin, and you know now how to do this. You add 273.15, okay? And the volume in liters is at standard temperature and pressure. And the standard temperature is 0 degrees Celsius, or 273.15 Kelvin. Pressure is 1 atmosphere, and you get then the mole volume of 22.4 liters, of 1 mole of ideal gas. Every ideal gas has the same moles, has the same number. No, has the same number of volume. If they have the same number of moles, you have the same number of volume. And this would be the mole volume of 1 mole of ideal gas. We did this at the very beginning. I showed you a big round thing which was about the size of the balloon when I popped these balloons. That's how we mixed the moles. So let me ask you another question. No, let's talk about temperatures first. So the temperature in Kelvin, so this is, what is it, 100 million temperature in Kelvin on the sun interior. You think it makes any difference if I say Celsius or Kelvin? 100 million? No, not really. Or the sun surface is 10,000 Kelvin or Celsius. Okay? The melting point of tungsten is about 1,000. That's the filament in these older light bulbs that we have, is tungsten. The water boiling point, we all know, is how many? 212 Fahrenheit, isn't it? Or 100 degrees Celsius, or 373.15 Kelvin. Melting point is 0 Celsius, 32 Fahrenheit, isn't that right? I didn't grow up in Fahrenheit. 32 Fahrenheit and 273.15 Kelvin. So the liquid nitrogen boiling point is 77 Kelvin, and so on. And you can get to very, very low temperatures. We talked about this. You can stop this, for example, the momentum of the atoms with a laser to cool it even further. Because movement means temperature, and temperature means volume. Okay? And so you can never reach absolute 0. But you can come very close. Even they come to 1 million millions now, actually. So 10 to the minus 12. So now comes the question. Let me give you the overview, because you need the overview here. You have an ideal gas. At the moment, all the gases we can treat as ideal gases, even if they're real at our conditions here. You have a 1 liter balloon, and you heat this balloon from 100 Celsius to 200 degrees Celsius at 1 atmosphere. So you do it right here. Okay, you don't change the pressure. It's still 1 atmosphere here outside. And what's the final volume of the balloon? Is it smaller than 2 liters? Is it 2 liters? Or is it larger than 2 liters? Why don't you think about it and give me your answer? There is a certain distribution towards A, but you need to confirm that if this is right, or maybe the other need to confirm that they are right. So what I'm going to show you, if I could have the blackboard, the light on the blackboard here, please, and the camera also. I wrote this morning for the other group, I wrote something down because they were a little bit more lost than you were, okay? P times V is N times R times T, okay? So we're dealing with two temperatures and what with two volumes, isn't that right? Okay. So P1, V1 is N1 times R times T1. And since N is the same, we haven't changed N, the number of moles we didn't change, it's the same gas, okay? So with this I can say V1, I bring this over here, V1 is N times R times T1 divided by P1. Okay, P1 is 1 atmosphere. It's a constant. N is the gas, I don't change the gas, and R is a constant to begin with. So I can treat this as a constant. I really am not interested with this. I can say V1 is the constant times T1. Right? I can do the same thing for the second volume. V2 is the constant times T2. With this, I bring this over here. I don't bring this down here. The T I bring down here. V1 over T1 is constant. V1 over T2 is a constant, and this is the same constant, okay? Because nothing has changed here. It's the same constant, so I say V1 over T1 equals V2 over T2. So far, just simple mathematical shuffling, all right? And now I want to know, what is my volume 2? The volume 1 was 1 liter. I know the temperature 2, the temperature 1. Now I know my volume 2. Now you can calculate it. Okay? Why don't you give me your new answer? Did you have this down here, the equation? This one? That's what you need. So we have a balloon has 1 liter, and we have it here. It's 1 atmosphere, it doesn't change. The same gas. We heat it from 100 degrees to 200 degrees Celsius. And I said already 1 atmosphere here. What is the balloon at the new temperature? What's the volume of the balloon at the new temperature? Where'd they go? Here, okay. All right, why don't you think about it and give me your answer? You got to have this down pat for the midterm, okay? Mid what, yeah. There is tomorrow, Greg Dellinger holds a review session here from 5 to 7. And I review everything in the next lecture on Friday. And everything I speak about on coming Monday will be not part of the midterm. But what I speak about on Friday will be part of the midterm, including the homework till Monday morning. We hope that the homework system will not go down again. Do it early. Got to click in? We still have a minute. The answer was A, that's correct. Now I explain to you why. Of course, it's smaller. You know what you did wrong, some of you? I told you before, this was the equation I derived for you. 100 degrees, and you use 200 degrees. Says 100 to 200, factor of 1 to 2. Okay, we got it. Must be double. That's wrong. You have to have it in Kelvin. 373.15 to 473.15 is smaller than 2, okay? This would be 2, but this is smaller than 2. With this, the answer is A, smaller than 2 liters. I see you on Friday.